Hello, my name is James Cheshire. I'm a PhD student at the Otto-von-Guericke Universitat Magdeburg, and along with my co-authors, Pierre Menard, who's currently at Inria in Lille, and Alexandra Carpentier, who is also at Magdeburg, we'll be presenting our paper, The Effect of Shape Constraints on the Thresholding Bandit Problem. Now, the thresholding bandit problem is a problem in multi-arm bandit theory. As is typical in such problems, you have a learner who is presented with several options or arms, and each one of these arms corresponds to a distribution. Now, the learner plays a game where each round of the game they must choose an arm and they then receive a sample from the distribution associated with that arm. Now, let's say each one of these distributions has a mean, and we'll say that for the kth arm, its distribution has a mean mu k. So here we have an example problem with 10 arms in total, and on the y-axis we have their mean, or the mean of their corresponding distribution, and on the x-axis we have the arm index. So basically the fourth arm here has a associated mean of roughly 0.5. Now, in the thresholding bandit problem, the objective of the learner is they're given a threshold tau, and they have to decide for which arms the mean of the distribution is greater than tau and which arms have a corresponding mean less than tau. So they want to identify this set of arms here greater than tau and this set of arms here less than tau. And in this example, we take tau equal to 0. We do this without loss of generality, and we'll be taking tau equal to 0 in all the examples during this presentation. So for simplicity, we're going to assume the arms are normally distributed with mean mu k variance 1, and we'll assume that for all k, mu k exists in the interval 0, 1. And then as mentioned, the learner is given some threshold tau, and their objective is to identify the set k such that mu k is greater than tau. So identify the set of arms who have a mean greater than tau. Okay, so to formalize the problem, we have k arms, a budget of t. So the budget t is the number of rounds of the game, so the number of samples the learner can draw from these distributions, and a threshold tau. So each arm corresponds to a distribution. At each round, the learner must choose an arm, and then they observe a sample from the distribution corresponding to that arm. And then once the budget is exhausted, so after capital T rounds, the learner has to output their prediction as to whether the means are above or below threshold. So if the learner thinks mu k is greater than tau, the kth value of q hat will be equal to 1. If the learner thinks that mu k is less than tau, then the kth value of mu hat will be minus 1. And obviously the learner is going to base these decisions on the information they gain from the samples that they've drawn during the game. So here we've got another example. So each black dot represents an arm. Again, the corresponding mean is the y-axis and the arm index is the x-axis. So the learner wants to identify these two sets, the set of red arms who have a mean above threshold and the set of blue arms who have a mean below threshold. So ideally in this setting, the learner would output q hat as -1, -1, -1, 1, 1, -1, etc. So now we've defined our problem, we'd like some way to measure the performance of the learner. So for this, we'll need a regret. So here's another example problem, again with 10 arms. And the learner has said that the arms in red are above threshold and the arms in blue are below threshold. But we can see they've made a couple of mistakes. So they've said that the third arm is above threshold when it's actually below, and that the sixth arm is below threshold when it's actually above. And we're going to base our regret off these distances here. So basically, we look at all the arms the learner misclassified, and we look at the distance of the means of these arms to the threshold, and then we're going to take the maximum of all of these distances. So in this example, the regret the learner suffers will just be this distance here, as it's the greater of the two. So to formalize this, if we let Q encode the true classification, we look at all the points where Q hat does not equal Q, and we take the regret as the maximum of the absolute value of mu hat minus tau across all of these points. Okay, so now we've defined the problem. The focus of our paper is to look at this sequence of sample means, so look at mu1 up to mu k, and see what happens when we enforce shape constraints on this sequence. You could also see this as the sequence of sample means is a discrete function, and we enforce constraints on this discrete function. So we consider 4 settings in total. So in the first setting, the sample means are unconstrained. They can do whatever they want. In the second setting, we assume that the sequence of sample means is monotonically increasing. So mu1 is less than or equal to mu2, less than or equal to mu3, etc., etc. In the third setting, we assume a unimodal constraint. So the sequence of sample means is monotonically increasing up to a single mode and is then monotonically decreasing. And in the fourth setting, we assume a concave constraint. So if you view the sequence of sample means as a discrete function, this discrete function must be concave. So if the learner knows which setting they're in, how are they going to be able to exploit this shape constraint to achieve a better performance? And that is what the focus of our paper is going to be. So let's start off with the unconstrained case. This has been studied in the literature in both the fixed confidence and the fixed budget setting. So we're working in the fixed budget setting because the number of rounds in the game, T, is fixed. And the primary focus of these papers is the problem-dependent regime, whereas we'll be working in the problem-independent regime. Now, in the unconstrained case, it turns out that an optimal strategy is to do uniform sampling. So you take your budget T and you divide it uniformly across the arms. So each arm is sampled K over T times. And from these K over T samples, you can generate a sample mean. And the idea is that you say this sample mean is close to the true mean. So here we have the true means as the black dots and the sample means as the red triangles. And we draw these error bands around the sample means, and we say that the true means will exist within these error bands. And then if we classify each arm according to its sample mean, so if the sample mean of arm K is above threshold, you say the true mean of arm K is above threshold as well, you'll suffer a regret at most the size of these error bands. And we can do this by applying a Houghton inequality with a union band, and we'll end up with the following upper band on regret, up to a universal multiplicative constant. So root K over T log K. Now the root K over T comes from the fact that we have T over K samples for each arm, and the root log K comes from the union band across K arms. Now we can also prove a lower band in this setting of the same order. In the unconstrained case, most of the interest lies in the lower band. Unfortunately, we don't have time to present lower bands during this talk. But regardless, we have a matching upper and lower band. So we have a minimax rate of root K log K over T for the unconstrained case. So moving on to the monotone constraint. Here we have this property that the sequence of means is monotonically increasing. Now this was first introduced in the following paper in the problem-dependent and fixed confidence setting in the context of drug dosing. But again, we'll be looking at the problem-independent regime and the fixed budget setting. So how is the learner going to exploit this monotonically increasing property? Well, an obvious choice is going to be a binary search. Now, noisy binary search has been studied in the literature, albeit in different settings with different structural constraints. But already from this literature, we can get a bit of an idea that a naive binary search won't be sufficient, and hopefully we'll get some intuition as to why over the next few slides. But first of all, let's just look at what a binary search does. So we take the midpoint of our arms. So here we have 100 arms in this example. So we take arm 50, we sample it a bunch of times, we generate a sample mean. Now, if this sample mean is above threshold, we can again say, well, assume the true mean is going to be close to the sample mean. Then we can use a monotonically increasing property to say, for all the arms to the right, their mean must also be above threshold or be above the lower bound on this error around the sample mean. So we can basically discard them, we can forget about them, just say they're above threshold, and focus on the arms to the left, which remain unknown. So again, we repeat the process, we take the midpoint again, this time it's below threshold, so now we go to the right, we again take the midpoint, and at every step of this binary search, we're removing half our remaining arms. So if the set of K arms gets decreased by a factor of a half at each step, it will take us a total of log K steps to end up with just a pair of adjacent arms. And the sample mean of one is above threshold and the sample mean of the other is below threshold. And then if we assume all of these sample means are close to their true means, we can then, again, bound regret on all the arms by the distance of this error band here. So basically we can say all the arms are going to exist in these grey rectangles. So if we say all the arms to the right of the pair are above threshold and all the arms to the left of the pair are below threshold, we'll achieve our bound on regret. So in the unconstrained case, we divided our budget across K arms, but now we just look at a subset of our arms, which is of size log K. So now we divide our budget across log K arms. So when we look at our bound on regret, this root k over t becomes a root log k over t, and this log k becomes a log k, because now we're doing a union bound across log k arms. And again, this bound is given up to universal multiplicative constants. But it turns out that a lower bound in the monotone case is of the order root log k over t. So this upper bound still isn't good enough. We have to do better. Primarily, we have to remove this term here, the log k term, which comes from the union bound. But at the moment, the union bound is necessary, because if during our binary search we have a sample mean that is very far from its true mean and we go in the wrong direction, we can never go back. So we're not going to be able to achieve a bound on regret. So we need some way to correct our mistakes. So the way we're going to do this is, at each step of the binary search, instead of just sampling the midpoint, we'll sample the leftmost arm and the rightmost arm. And if we detect an inconsistency, if something seems funny, we can backtrack to the previous step of the binary search, and this will allow ourselves to make a mistake. So to illustrate this, it's best to view our arms as a binary tree. So here we have a setting with 5 arms, and we're going to map it to a binary tree in the following way. So the first node of the binary tree will be the set of arms 1 to 5. The left-hand child will be the set of arms 1 to 3, and the right-hand child will be the set of arms 3 to 5. So we can see our binary search as a walk on this binary tree. We start off, we sample the midpoint, which is the third arm. If the sample mean is above threshold, then we go to the left-hand child, and this is our new set of arms. And we continue until we reach a leaf, and we hope that we reach the correct leaf, which is the pair of adjacent arms 2 and 3, either side of the threshold. So how is our binary search with corrections going to work? Well, as mentioned, at each stage, we sample 3 arms, the left, the middle, and the right. We sample each one of these arms approximately log k over t. And for a given time step, we're going to define a good decision as the event that for each one of these arms, their sample mean is close to the true mean. Okay, so let's do an example of this binary search with corrections. So in the first step, we sample our 3 arms, but the middle arm, arm number 3, is far, the sample mean is far from its true mean. The sample mean is below threshold, whereas the true mean is actually above threshold. So we go the wrong way. In the naive binary search, it would be over by now, we'd be screwed. But luckily, we're doing this binary search with corrections. So on the second step, we end up sampling the third arm again, because it's now the leftmost arm. So we sample it again. We realize that there's an inconsistency. We've made a mistake somewhere, because now we actually sample it correctly. We make a good decision. Well, the sample mean is well concentrated. So we think, okay, there's been a mistake made. So we backtrack back up to the parent node, and we repeat the binary search from the start. This time we make good decisions, and we end up where we want to be. So the idea behind the proof is that we don't have to have all our decisions as good decisions. We don't need a union bound on all decisions being good. We just need the majority of good decisions to be good. So we can make some mistakes as long as we have enough good decisions to correct them. And this sort of relaxation will allow us to lose this log k bound in the regret. And then we'll have a matching upper and lower bounds, so we'll be able to achieve a minimax rate of root log k over t. So to conclude, we have the unstructured and monotone settings, where we have the minimax rates of root k log k over t and root log k over t, respectively. Now, unfortunately, we don't have time during this talk to go in detail for the unimodal and concave settings, but we can have a little think about what the minimax rates might be. So in the unimodal case, if we knew the mode, then we could separate this problem into the monotone setting, because we have a monotonically increasing sequence and a monotonically decreasing sequence. So we'd think that maybe the minimax rate might be the same as the monotone setting. But it turns out that the problem of finding the maximum is actually harder than the thresholding problem in the monotone setting. So the minimax rate ends up being dominated by the minimax rate of finding the maximum. And that's root k over t. Now in the concave setting, we again have a monotonically increasing sequence and a monotonically decreasing sequence. But we also have this concave property. And it turns out that the learner can exploit this concave property to perform a binary search, but on a log scale. And this allows us to get the minimax rate of root log k over t. Okay, that concludes our talk. Thank you very much for your attention. If you have any questions on what was presented or on the 2 cases we didn't have too much time to go into, you're very welcome to join our poster and question and answer session later on. Thank you very much.